Here is a second example of an optimization problem. So in this problem, you have been recruited by a manufacturer who wants to build a 500 cubic foot rectangular tank by welding together stainless steel plates. The tank has a square base and an open top, and the manufacturer wants the tank to weigh as little as possible. What dimensions do you recommend they use for the base and height? All right, so first things first here, we need to sketch our scenario. So we need to draw a rectangular tank. All right, so bust out your art skills and sketch a tank or just some rectangular prism. All right, so there we go. I'll give it a little 3D look here. Okay, there's a rectangular tank. And we also want to introduce our variables and label different components of this tank. So we have generally for a tank like this or a rectangular prism, we have dimensions of length, width, and height. We can label those since this tank has a square base. This dimension and this dimension are going to be the same. So let's just maybe call those X for the base. And this height of the tank doesn't have to be the same. It's not necessarily a cube. So we'll call that Y. Okay. And you can use whatever variables you want, just X and Y, that's what I'll go with. But if you wanted to do like W and H or whatever, that would be totally fine, just as long as you can keep them straight. Okay, so we've drawn our sketch, we've labeled it, we've introduced our variables. Now let's identify what our goal is in this problem. So the goal here. Okay, and when you're doing this goal type of thing, remember you are thinking about whether you want to maximize or minimize something, and then what that something is that's getting maximized or minimized. So when we're looking through this, we can see the final answer we're going to give is the dimensions of the tank. Okay, but that's not really maximizing or minimizing there. So then we back up a little bit and we see the manufacturer wants the tank to weigh as little as possible. So that is a goal that is minimizing something there, minimizing the weight of this tank. So you can even write that to begin with. Minimize the weight of the tank. But coming up with an equation for the actual weight of this could be kind of difficult because remember that's your next goal or your next step after identifying your goal is to come up with an equation for your quantity of interest. And coming up with an equation or a formula for the weight of the tank could be challenging. You'd have to figure out how much stainless steel you're using, and then maybe multiply by like the density of stainless steel, and you'd have to go look that up. So instead of doing that, let's think of how we can minimize weight in a simpler way here. So in that, like thinking about the weight process there, you'd need to see how much stainless steel you are using. That's going to affect the weight of the tank, right? So if we're minimizing the weight, we could also think about that as minimizing the amount of material that we're using. Okay, because if we use less stainless steel, then we're going to have a lighter tank. And the material used here is in the construction of the sides and the base of this tank here. And those are the surface area of this tank. Okay, consider, the thickness of each plate to be negligible here, but we are trying to minimize surface area because that's what's contributing to our material usage. And that is something that we can actually come up with an equation for fairly easily. Weight, not so much. Material used, maybe not so much, but surface area, yeah, we can get that. So I'm going to call that surface area, let's call it S for surface. And the equation for this, you have to do a little geometry here, bear with me. All right, our surface area is just going to be the areas of all the sides of this tank. So notice how we've got 4 of these vertical sides here. And each one has an area of x times y. So you have xy on that side, over here, in the back, and then the front side is really hard to draw there. So you have 4 of those upright sides, 4 of those xy areas. So these are the 4 sides. And then we've also got the base of our tank down here. Okay, and you'll notice that the base is an area of x times x. It's a square base down there. And so the area is x squared. Okay, so we've got the 4 sides and the base. And that's actually also why it's important that this problem said the tank has an open top, because otherwise we would need to add another x squared to cover the top of the tank here. But we don't need to add that extra piece in this case. So it's just one of those x squared terms. All right, so there's our equation for the surface area. S equals 4xy plus x squared. And we can see here that, yes, it is a function of 2 variables right now. S is a function of both x and y at the moment. And that's not going to help us when it comes to taking our derivative, finding our critical points. So we've got to use some other information to get this somehow in terms of just one variable. Okay, so let's see what other information we're given here. All right, you have been recruited by a manufacturer who wants to build a 500 cubic foot rectangular tank. We haven't used that number yet, and that's exactly what we're going to need to use. That 500 cubic feet right there is our given information for the volume of this tank. So that's our constraint equation. Okay, if I can spell constraint, there we go. So our given information, the constraint to this problem is the volume of the tank is 500 cubic feet. All right, so the volume of this tank in terms of our variables would be length times width times height. That would be x times y. Okay, so V, oops, there went my base. Da, da, da. Okay, so V would equal x squared times y. All right. And since we know that volume is 500 cubic feet, that tells us that 500 equals x squared y. All right. Now we want to solve for one variable or the other here, so we can plug it back into our S equation. And there is an easier choice here, like one variable is easier to solve for than the other. it's going to be a lot easier to solve this for y rather than x. We're not going to have to mess around with any square roots or whatnot if we do that. So just divide both sides by x squared. Y would equal 500 over x squared. Okay, we're going to take that and put it into our S equation. Okay, so let's do that. So S is going to equal 4xy plus x squared, but we just found out that y was 500 over x squared. So that's 4x 500 over x squared. Okay, that's going in for y right there, plus x squared. And you can actually do a little simplification now. Cross out one of those x's. Okay, that x with one of those. And you can multiply 4 times 500 as well. You'd have 2,000 over x plus x squared. All right. And now you can see that s is just a function of the variable x only, not x and y anymore. In order to make the next step easier, you could even write this as 2,000 x to the negative 1 plus x squared, because you know what's next. We're going to take a derivative and look for some critical points. Okay, so let's do it. All right, derivative s prime. This is the derivative of s in terms of x, ds dx. All right. So a little bit of power rule here. You'd have negative 2,000 x to the negative 2 power plus 2x. Okay. And let's see. Let's get that in a slightly more workable form here. Negative 2,000 over x squared plus 2x. And let's see, to make numerator and denominator really clear here, I think I might put that in terms of just a single fraction. Okay, so I'm going to multiply this guy by x squared over x squared. Then we would have negative 2,000 plus 2x cubed over x squared. And that would put it all into one rational expression. That'll make it nice and easy to find our critical points. It wasn't necessary, by the way, to put that into a single expression. You can still find your critical points just from the form of the derivative that we had before. This will just make it a little easier. Okay, so critical points. Look at where s prime is undefined. And that's why it's kind of nice to have it in a rational form like that. This is where x squared would equal 0. And so that would give us x equals 0. But if you think for a second about what x actually is, that would be the dimension of the base of this tank. And if you think about x equaling 0, that is not really a situation that is going to physically work. You're saying that the base of this tank is 0 feet by 0 feet, and that is not going to give you the volume that you want here. So this critical point, although it is a critical point, it's not really one that we're going to use. I guess yeah, this would also be one of the endpoints of our domain. So that's another reason why it's not a critical point. So this is not physically valid, and it's also one of the endpoints of the domain for x. So we're not going to end up really using this critical point there. well, not really much of a critical point. Not physically valid. We need x to be greater than 0. Okay, so let's focus instead on where s prime is equal to 0. That would be where negative 2000 plus 2x cubed equals 0, taking the numerator of our expression there. And so 2x cubed equals 2000. That would mean x cubed equals 1000. And cube root both sides. That would give us x equals 10. Okay. So let's check here just to make sure that this is actually going to give us what we want, because remember, our goal in this is to minimize the weight of the tank or minimize the surface area. So we need to make sure that this truly gives us a minimum for S. And remember that we can test that by using a little number line for the derivative s prime. There's 10. And test either side of that, okay, with any number that is less than 10. Plugging it into the first derivative expression there. I might think of the number 1, I think. So if I'm thinking about x equals 1, negative 2000 plus 2 divided by 1 is going to be negative 1998. So that would be definite negative over positive, giving us a negative result for the first derivative there. And then think about a number that is larger than 10, like 100, for instance. You can do whatever you want over on that side. If you take that number and plug it into the first derivative there, it will overshadow this negative 2000 in the numerator to make the numerator positive, and the denominator is also still positive. So we got positive over positive, and that's a positive first derivative overall. So we have a decreasing surface area function and then increasing. Goes like this, then goes like this. And so that shows us that yes, 10 is truly going to give us a minimum for the surface area function. So yes, this gives a minimum. Cool. All right, so that is doing what we want here. So from that, we can build our solution. Okay, our dimension x is going to be 10, unit is feet, y is the height of our tank, and we have a convenient expression for y right here. Okay, y is 500 over x squared. Okay, y equals 500 over x squared. Okay. Remember that 500 is actually coming from the volume of our tank. So units wise, that volume is 500 feet cubed. So you can put that in if you're keeping track of your units here. That would be 500 cubic feet divided by x is 10 feet, and that is getting squared. So you'd have 500 feet cubed over 100 feet squared. That would give you 5 feet. Okay. And now to give the manufacturer what they really want here, our final answer was supposed to be dimensions of our recommendation for the base and the height. So the base is x by x, and then the height is y. And so we would say dimensions are going to be base of 10 feet by 10 feet and a height of 5 feet. And that's our final answer on this one.